Let's pretend for a second that you're looking for a treasure. You're looking at your map, and you put your compass on the map. You put it right, let's say here, and it's pointing this way. And then all of a sudden, for whatever reason, strangely, the compass needle starts pointing this way. And then a few minutes later, it points back the way that it was pointing before. And then a few minutes later, it's pointing this way again. And then you turn your paper, and the compass needle is pointing this way. And then a few minutes later, it's pointing this way. What's going on? Well, you realize the only thing that's changed in that whole process is that little wire that you had running underneath it that ran to a battery and a little lamp or a flashlight or something, okay, your iPhone charger, whatever the case may be. You realize the only thing that's different is that wire was running underneath it, and sometimes there was an electric current flowing through that wire, and sometimes there wasn't. When there was not an electric current flowing through it, you found that the compass needle pointed this way. When there was an electric current pointing through it, you found that the compass needle pointed this way. What's your conclusion? What's your conclusion if the only difference in this whole scenario, when the compass needle started pointing in different directions, was that there was either an electric current on in this wire that goes underneath this map, or an electric current off in this wire? What's your conclusion? Yep. Good. Whenever you get an electric current in a wire, or whenever you have moving charges, you're going to generate a magnetic field. And that magnetic field is going to be stronger than the Earth's magnetic field, just like the bar magnet magnetic field was stronger yesterday. And that's going to affect the current, it's going to affect the compass more than the Earth's magnetic field will. Go ahead. This phenomenon was discovered in 1819 by a guy named Hans Christian Oersted. I would argue that this is one of the single most important scientific discoveries as far as technology goes, as far as implementing a scientific discovery in technological applications. Arguably one of the most important discoveries in the history of the world. Just about everything we use now, everything technology-wise, technology-based that we use, is at least largely in part based on this principle, that electric current generates magnetic field. Even just moving charges generate magnetic field. They don't have to be in a wire. It has nothing to do with the wire. Wire is usually copper or aluminum, which isn't magnetic. As long as you have moving charges, you generate the magnetic field. This is a huge, huge deal. You don't have iPhones if you don't have this discovery. You don't have headphones if you don't have this discovery. You don't have speakers, or you don't have fans or TVs, or just about anything that's technology-based is not going to exist without this discovery. And other things as well, of course. We know the direction of a magnetic field surrounding a bar magnet, right? We established that yesterday, and we reviewed that earlier today as well. What does the magnetic field look like surrounding a charge moving through a wire, or just a charge moving through the air for that matter? Before we talk about that, I might actually define two new symbols for notation. If I want an electric charge moving to the right, or a car moving to the right for that matter, then I'm simply going to use an arrow to the right. If I want it moving to the left or up or down, then you know how you're going to draw that, right? But what if it's coming towards you? What if it's going away from you? What is the symbol that we're going to use to represent that direction going to look like? I'll tell you a little story about when I was 4 years old. About 4 anyways, give or take a little bit. Had a friend across the street. He was, I think, 6 maybe. And we would play in his basement a lot. And his friend across the street had a cool basement. I mean, I grew up in rural Nova Scotia. Like, in rural Nova Scotia, people's basements were concrete with stuff in the basement. It wasn't, fancy, wet bars and pool tables and whatever. Anyways, my friend had a pool table in the basement, and he had dartboard, and he had all kinds of cool stuff, okay, which most people didn't have. So we'd spend lots of time in the basement. One day I remember we were down there at 4 years old, or I was 4 years old, playing darts, unsupervised, playing darts. And I remember not being very good. He was a little bit better than I was, but he still wasn't very good either. Throwing darts at the dartboard, and for the most part, a lot of times he's just missing the dartboard. But when you hit the dartboard, usually what would happen is the dart would kind of hit it from the side like this, and then just fall, right? If you even hit the dartboard. I don't know. I don't even know if I got one stuck in there. I might have. I'm not sure. But I remember at one point missing the dartboard, or at least banking it off the dartboard and not sticking in anyways. I remember going to pick up the dartboard. So I bend over to pick up the dart, and as I stand up to pick up the dart, I feel this in my back. So my 6-year-old friend couldn't manage to stick a dart in a dartboard, but he managed to stick a dart in my back. Talk about getting stabbed in the back, eh? Literally, it stuck in my back, and we had to pull the dart out of my back. Now, it hurt a lot, but I never saw it coming, right? Because I was facing the other way. I may have even cried. I'm not sure. Might have cried when I was 4 years old. I wouldn't cry now. Listen, if I got hit by a dart now, I wouldn't cry. I promise you. But 4 years old, I might have cried a little bit. Didn't see it. But you know what I do? Like when I'm looking at the topic that we're looking at right now, and this whole magnetic field and direction coming towards you, going away from you, I picture it. I picture that event as if I could have seen the dart coming towards me. When a dart is coming towards me, what do I see? Okay, what do you see? I see the tip of the dart, right? I see the point of the dart coming towards you. Looks like this. Now, I'd rather picture the dart going away from me, at him. No. It was an accident, I'm sure. If he had wanted to hit me with a dart, he couldn't have possibly hit me with a dart because he wasn't that good. I want to picture the dart going away from me. When I picture the dart going away from me, what do I see? I see the fins on the dart, right? The feathers on the dart. So it looks more like this. This is the symbol for anything coming towards you, a dot. It might be a car driving towards you. It might be a dart coming towards you. It might be an electric charge coming towards you. A dot represents coming towards you. An X represents going away from you. And again, I remember that. From the time that I learned this in high school, through university, even now, the way I remember that is, when I'm 4 years old, when there's a dart coming towards me, it's going to look like this. When I'm 4 years old and there's a dart going away from me, it's going to look like this. All right? Now, let's draw a negatively charged particle that's coming which way? Away from us or toward us? Toward us. Let's draw a negatively charged particle coming towards us. Okay, we'll make it an electron, negatively charged particle. Some kind of negatively charged particle, at least. Turns out the shape of the magnetic field is circular. Here's one magnetic field line that surrounds that charged particle coming towards you. So if this pen right now is a charged particle coming towards you, the magnetic field goes around it like this, circular like this. That's one magnetic field line. Now, here's another magnetic field line. Here's another magnetic field line. Here's another magnetic field line, kind of running out of shape here. What do you notice about those magnetic field lines? They're circular, right? What else do you notice about them? How does the proximity of the field lines here compare to the proximity of the field lines way out here? They get further away from each other, right? What does that tell us about the strength of the magnetic field? It decreases. The density of the field lines, way back in Physics 20, we talked about gravitational fields. The density of the field lines represents the strength of the field. As they get further and further away from each other, the weaker the field is. That should make sense, right? If it's the current inside this wire that's causing a magnetic field, then the further you get away from it, the weaker it's going to be. about direction? What about the direction of the field? Because it's a vector field, right? It has to have a direction. We're going to use a rule that we call the Wiregrass rule to figure out the direction. This is what Rucker was referring to a little bit earlier. There's a number of different hand rules, and different people have different versions of hand rules. Okay? Different teachers even use different versions of hand rules. Different textbooks use different versions of hand rules. Okay? I like the hand rules that they use in your textbook. There's a lot of things that I like about that book. There's a lot of things that I don't like about that book. One of the things that I do like are the hand rules they use. We don't necessarily call them the same thing, because sometimes their terminology isn't the greatest, okay, but the rules themselves work well. The first rule, they call it the Wiregrass Pool. We're going to call it the Wiregrass Pool as well because I think it works well. Here's how it works. You're going to take your hand, your left hand if it's a negative particle, your right hand if it's a positive particle, and you're going to stick your thumb in the direction that the particle is moving. So we got a particle now coming towards you, going out of the board towards you. I want everybody right now, everybody to do this. Take your left hand, put your left hand in, you put your left hand out, put your right hand in, now shake it all about. Let's do that. No, never mind. Everybody have their hands all ready to go here? Okay, left hand, left thumb. Stick your left thumb towards the back of the room because that's which way the particle is moving right now. Guys, listen, you got to do this. Okay, you can't just watch somebody else do this. Okay, if you watch somebody else do this, you're going to go home tonight thinking, oh, I know that. That's easy, right? But then you're not going to do it. You're not going to be able to do it. Okay, you have to physically do this with your hands, everybody. Put your left thumb pointed towards the back of the room. That's out of the page, right towards you guys. Now I want you to bend your fingers. You don't have to scrunch them up like this, but you can scrunch them up like that if you want. There's no rule that says how much you have to bend your fingers. You just got to bend your fingers. Your fingers will point in the direction of the magnetic field. But wait a second. I'm looking at Aiden's fingers. They're pointing straight down right now. I'm looking at your fingers. They're pointing kind of like this. I'm looking at your fingers. They're kind of like that. They're all pointing in different directions. But look at this. Okay, if I stick my thumb out really close to the board here, if I stick my thumb out of the board and I bend my fingers a little bit, and my fingers are above the charge, then they're pointing to the right. But wait a sec, somebody bends their fingers a little bit more and they're to the right of the charge. Which way are my fingers pointing now? Down. But wait a second. I bend my fingers even more, my fingers are below the wire, or below the charge. Which way are they pointing now? To the left. It doesn't matter where you put your fingers. It doesn't matter how much you bend them. Your fingers, all of our fingers there, we're pointing clockwise according to this. Does that make sense? So we've got a magnetic field that's circular in nature, and it's pointing clockwise. Remember, I'm going to write a little summary here of the Wiregrass Pool. Your thumb points in the direction of the moving charge. Whether it's in a wire or not, the direction of the moving charge is where your thumb goes. Now remember, if it's a negative charge, you're going to use your left hand. If it's a positive charge, you're going to use your right hand. An alpha particle, a proton, we do the exact same thing we just did, except you would use your right hand. Your bent fingers, or your grasp, right? You're grasping that wire with your bent fingers. They're pointing in the direction of the magnetic field produced by the moving charge. Now, Rucker was talking about the left-hand rule earlier. Now, I'm not sure whether he meant this left-hand rule, because this is a left-hand rule, but there's also a couple more left-hand rules as well that we'll talk about in the coming days. Not today, though. Okay, the Wiregrass rule is the first one. We call that sometimes a left-hand rule. because you're using your left hand if it's a negative particle, a right-hand rule if you're using a positive particle. Let's try another example of this, okay? Let's say we've got a charge that is an electron again, moving, which way is it going this time? Georgia, which way is that charge going? Represented by an X? Good, it's going away from you. Now, the shape of that magnetic field is circular. We could draw, right, a dozen field lines, but in the end, we don't really need to draw a dozen. 1 or 2 is fine here. What's the direction of the magnetic field here? This time you're going to stick, everybody do this, please. Stick your thumb in the direction of the particle. Now, as you're doing this, I see everybody putting their hand up like this, pointing it towards the front of the room. You guys all have this drawn on your page right now. If you want to do it relative to your page, go ahead. Okay? Stick your thumb into your page as opposed to into my page. When you do that, you're going to find still that the magnetic field is going to go counterclockwise, no matter where you put your fingers. If you put your thumb into the page, like straight into the page, not something like this, like, right? Put your thumb straight into the page, okay? Keep your thumb perpendicular to your hand, and your fingers should point counterclockwise. Whether it's your page, whether it's my page, no matter where your fingers are, they should put counterclockwise. See? That makes sense, Aiden? Going counterclockwise there. So in this case, we'd say it's counterclockwise. Got it? I got one more example for you, and then I'm going to leave you with just a tiny bit of homework. Here's a wire that has electrons going through it. This wire generates a magnetic field, but the magnetic field here is a little bit harder to draw. It's circular magnetic field, but it's like this, right? Here's the wire. The magnetic field is going around like this. So kind of draw it like, it's hard. That's hard to draw, right? Do you see what I'm trying to do there, though? What's the magnetic field look like at point A? What's the magnetic field look like at point B? Above the wire, below the wire. What's the magnetic field look like at point C, in front of the wire? What's the magnetic field look like at point D, in back of the wire? Well, take a ruler, take a pen, take something. This is my wire. I got an electric current going this way in that wire. Let's stick your left thumb in the direction of that current, to the left, towards to the right. It's your right, I guess, my left. Let's bend my fingers. Bend my fingers how much? Well, bend your fingers as much as you need to. Bend my fingers right now to the point where they're my fingertips. Looking at your fingernails here, not your whole fingers, right, because they're bent. Look at your fingernails. Right now, my fingernails are above the wire. Which way are they pointing when they're above the wire at point A? Which way are they pointing, Brad? Towards the front of the room, right? Would say into the page, right? For you guys, it wouldn't be towards the front of the room because it would be on your page. It's drawn differently, right? For you guys, it would be down. Well, into the page works for you and for me, right? Our frame of reference is the page. The magnetic field is into the page. Now at point B, down below, put your fingers down below. Bend your fingers enough or twist your hand enough so that your fingertips are down below. Which way are they pointing? Here's the page. Which way are they pointing? No, they're not pointing up. They're pointing out of the page. Right? They're pointing out of the page. Right now, my fingers are in front of the wire. Which way are they pointing? You could say up, but we don't want to say up because for you guys, your page is oriented differently, right? So for you guys, that would be forward, right? But we could say, both of us can say it's toward the top of the page. And now back here, we would say it's toward the bottom of the page, right? That makes sense? You got a couple of options. You can figure out what the direction of the magnetic field is at one point and then just kind of trace it around with your finger like this. Or you can do what we just did and figure out what it is at all 4 points. Does that make sense? Oh, perfect timing. Here's what your homework for tonight is. Yeah, seriously. Worksheet number 10. The good news is it's like 5 questions involving a hand rule, left-hand rule or right-hand rule. So pay attention to that. Circle in red whether it's a negative or positive particle, so you remember which hand rule to use. All right, that's it for today, guys.